Cooper's Law. The first transmissions. Guglielmo Marconi conducted his first transmissions in 1895. The energy from his spark gap transmitter occupied a huge band of radio spectrum. This means that the conversation in a given locations were minimal. By 1901, his first transatlantic transmission blanketed an area of millions of square miles. It was capable of sending pitiful, small amounts of information. Using that technology, only about 50 separate conversations, whether broadcast or personal communications, could be accommodated on the surface of the earth. Cooper's Law. Martin Cooper, known for inventing the handheld cellular, found that the ability to transmit different radio communications at one time and in the same place has grown with the same pace since Guglielmo Marconi's first transmissions. Cooper's Law of Spectral Efficiency. The number of such communications being theoretically possible has doubled every 30 months for 104 years. As you can see, the rate of improvement in the number of communications has constantly increased, and it is projected that by 2020 we can reach more than 1 trillion conversations per location. This means that since the 1980s, the number of conversations that can be held at a single time has improved 1 million times. Technology behind the law. Frequency division, modulation techniques, spatial division, spectral reuse. Frequency division is also known as frequency division multiplexing, which refers to the sharing of a channel by dividing up the passband of the channel into multiple subbands. Each subband can carry a signal conveying data. The bandwidth, not the passband, allocated to the channel determines how much information the channel can carry. Thus, subbands of equal bandwidth can carry the same amount of information. As long as the various input signals contain frequencies only in their designated subbands, all their inputs can be transmitted simultaneously without interfering. The principle of frequency division multiplexing is best applied in broadcast radio. This is because each station is assigned its own transmitting frequency. Modulation techniques. These are the methods that are used to encode digital information in an analog world. The three basic modulation techniques are AM, amplitude modulation, FM, frequency modulation, and PM, phase modulation. Amplitude modulation modifies the amplitude of the carrier to represent ones or zeros. In the above example, a 1 is represented by the presence of the carrier for a predefined period of 3 cycles of carrier. Absence or no carrier indicates a 0. The advantages are it is simple to design. The disadvantages: noise spikes on transmission medium interfere with the carrier signal. Loss of connection is read as zeros. Frequency modulation modifies the frequency of the carrier to represent the ones or zeros. In the above example, a 0 is represented by the original carrier frequency and a 1 by a much higher frequency. The cycles are spaced close together. The advantages: immunity to noise transmission medium. There is always a signal present and the loss of signal can be easily detected. The disadvantages: it requires 2 frequencies and detection circuit needs to recognize both frequencies when signal is lost. The carrier phase is switched at every occurrence of a 1 bit but remains unaffected for a 0 bit. The phase of the signal is measured relative to the phase of the preceding bit. The bits are timed to coincide with a specific number of carrier cycles. 3 in this example equals 1 bit. The advantages: only 1 frequency is used and it's easy to detect the loss of a carrier. Disadvantages: complex circuitry is required to generate and detect phase changes. Mobile stations operating outside the bounds of these directed beams experience a near-zero interference from other mobile stations operating under the same base station with the same radio frequency. Since beams are focused, the radio energy frequency can have increased base station range. This attribute of SDMA allows base stations to have larger radio coverage with less radiated energy. This narrow beam width also allows greater gain and clarity. Under traditional mobile phone network systems, the base station radiates radio signals in all directions within the cell without knowledge of the location of the mobile station. SDMA technology channels radio signals based on the location of the mobile stations. Through this method, SDMA architecture saves on valuable network resources and prevents redundant signal transmission in areas where mobile devices are currently inactive. Spectral multiplexing is an application of a coherent processing to create two or more distinct spectral channels on the same time frequency radio resource. The multiple spectral channels can be used to enhance the link reliability or data rate to or from a single client device, also known as MIMO layers, or to establish simultaneous link to or from multiple client devices, also called spectral division multiple access or SDMA. Both approaches improve spectrum reuse and enhance network capacity. An FCC initiative that licenses secondary users for many channels on the basis of non-interference with the primary users in an effort to reuse the radio spectrum over time. The spectral reuse refers to the recycling of channels of radio. This approach results in multiplications of effective capacity of spectrum in a given area. One good example of spectral reuse happens when you travel to another state. If you listen to your favorite radio station in Texas, it is probable that you can listen to it within state boundaries. However, if you go to another state and try to get your favorite radio station, then you'll see that your station is gone. What happened here is that the FCC contained geographic areas within a cell. Then if you leave that cell, you'll encounter new transmissions in that same channel. The FCC now creates smaller cells. This means that instead of using the state geographical area, it uses the city geographical area. This creates new transmissions and enables multiple communications. Most of the improvements as suggested by Cooper's Law have been achieved using this technique, because spectral reuse provides the flexibility to deploy and illuminate each sector independently. Service providers are able to radiate only in the specific direction in which subscribers are located. This capability for flexible deployment gives service providers the ability to maximize return on invested capital, provides a fully accessible wireless broadband infrastructure, enables greater aggregate data throughput, sustainability reduces the adjacent sector, and cell interference common to traditional antennas. In conclusion, Cooper's Law is really helpful in identifying and understanding the past and the future communications. With this law, we can develop technology that can sustain the future of our communication systems.